More electrical principles. And now we're going to talk about some of the new stuff they've added, or at least added more, on skin effect and real and reactive power and the electrical length of conductors, which is the question I can't explain. So real power is the actual amount of power that's being dissipated in the circuit. Like your 100-watt light bulb is dissipating about 100 watts of power, less light, but as far as the electric company is concerned, it's 100 watts. If you have devices in your house, such as refrigerators, air conditioners, anything with a motor, it's going to have an inductive reactance in it. So that means you're going to have a phase angle and phase shift, and you're going to have an apparent power, which is the product of the voltage and the current. So it's the length of the vector. The real power that's being dissipated is what's going to be on the x-axis for R. So the more inductance that you have, the longer that apparent power vector is. That's actually what the power company charges you, where you may be using much less real power because the reactive power is imaginary, because it's on both sides of the axis, positive and it's negative. And we also can talk about power factor, which is the cosine of the phase angle between the voltage and the current. So that'll be a number somewhere between 0 and 1. And I remember years ago, there was a NASA guy that invented a power factor correction device that was fairly simple, and you could install it in your house, and it would correct your power factor so you looked like you were purely resistive. So it lowered your electric bill because they were charging you for imaginary power because there's more money in that. Well, the green bar is still there, so obviously it wasn't the sharing. If you plot voltage versus current for an inductive reactance and a capacitive reactance, you can see the positive phase shift and the negative phase shift. So these are 90 degrees apart.
Which means EL and EC are 180 degrees apart.
And if they were equal,
They would.
What would the result be?
You would cancel each other out.
Right. If they're not equal, then you're going to have a phase shift one way or the other. So true power is measured by using the I squared R or E squared over R formula for Ohm's law, because that will give you true power. Whereas if you use E times I, it will give you apparent power if there's phase shift involved. Since we're doing it based on the current or voltage across the resistor, it's pure real power. So you can do the reactive power if you know what the reactance is, and use I squared X or E squared over X. And that will give you the portion of it that's reactive power. In other words, the vertical, if you plotted apparent power, real power, and imaginary power. And we call that volt amps reactive, or VARs. I remember in college, I worked for a power company, And we had a big network simulator to simulate the entire state. And they were getting ready to put in a 475 kilovolt power line that was, I forgot how many miles long. And we simulated that without any loads on it, just an open power transmission line. And it was 2 megavars.
Just because of a,
Just because of the capacity and inductor, I forgot which way it was. But it was only about 4 amps at 500,000 volts. And then the apparent power, like I said, is the vector portion. So you could do it as I squared times the magnitude of the impedance. This is a circuit that's showing pure real power because it's purely resistive. So we have 120 volts across the 60 ohm resistor. So we're going to have 2 amps flowing. So you can calculate what, with any of the 3 formulas, you're going to get the same answer. And if you plot it, you're going to see that the blue is the voltage. The dotted red is current. They're in phase because we have no reactance. And if you do the real power, you see that it never goes negative. It's real power. So the average power is going to be like 0.707 of the peak. We'll get into RMS later, I suppose. If, and we'll have another one coming up showing reactive power. And they say it's non-productive because it is actually imaginary. It doesn't do any work because the power, you're charging inductors and capacitors, so the energy is just going back and forth. So in theory, there's no loss or no dissipation.
so just to clarify, real power is never a negative number.
Right.
Okay.
Because there's a thing they call negative resistance. It's not truly negative. It's the slope of the line changes.
Okay.
If you have a example is a switching power supply. As the load on the power supply increases, well, excuse me, I mean, forget about the load. If the voltage into a switching power supply drops, the current will increase. Ohm's law says that if I decrease the voltage, the current's going to decrease. So it's a negative reaction, but it's not really a negative R.
Okay.
Okay. Because it's trying to maintain a constant output power. So it's got to have at least that much power coming in. So if you have a lower voltage, you've got to have more current. So power in is equal to power out minus loss.
Okay.
Okay. So what is reactive power? Useless. Okay, so if I have a circuit with just an inductor instead of a resistor, I apply my 120 volts, I'm going to get a current through it. And if I can go through the formulas, I'm going to come out with a positive 238.8 VARs, volt amps reactive. Because that 60 hertz frequency, it's looking like a 60 ohm reactance. Well, I thought that's reflected. So what happens to reactive power in an ideal inductor or capacitor? Where does it go?
Oh. I mean, I think it's D. But that pointer is
Oh,
on.
well, that's not.
Hey, I'll take it. So it's stored,
Right,
And
does
then-
it generate heat?
so it's not dissipated, so it would be. Right? Does it generate heat?
No, doesn't generate heat.
So it wouldn't be A.
If it was a pure inductor. In the real world, it's gonna have a little bit of resistance, so yes, it would generate.
Okay.
So it's just energy stored
Mhm.
in in this case, it was the magnetic field. And because the voltage is going positive and negative, okay, it's gonna store energy on the positive cycle,
Mhm.
and then it's gonna come back and it's gonna store energy in the opposite, but still in the magnetic field.
Okay.
So it's the same amount of energy, it just sort of
Okay.
doesn't do anything useful.
Does it? Is that what you're asking?
No, it
It
doesn't.
does. It doesn't.
And this is the chart I probably should have had before that one. Where this is the inductor that had 60 ohms of reactance. And you can see that current over here, okay, is lagging the voltage. Remember Eli, the Iceman? And if you look at the power, the green line,
Mhm.
okay, it's equally positive and negative. So the average power is what? So what's the phase relationship between current and voltage for reactive power?
Green phase. The 90 degrees power phase. Yeah, 90 degrees power phase.
Well,
What can it be?
it would have, I mean, based on the question, if C or D was correct, then A would also be correct. So they would have to be B, just by the way the question is worded.
Very clever. Yes.
It must be B.
Read all answers before you answer.
But the question is, that's not the right answer. That's what's weird. B is not the correct answer. That's what's weird about that.
Oh. Okay, so C was right.
So the thing is, what they're not asking you. The thing about that question is they're saying, what is the phase relationship? They want you to compare, not just say that they're in or out. They want you to give a number.
Right. And they're 9 degrees opposite.
Because it's a pure inductance.
So that's what they allow you to restrict that. Yeah.
Yes.
You gotta pay attention to that question.
Yeah. There's a few like that.
Yeah.
Okay, so if we have resistance in the circuit, we are going to dissipate some power.
I see.
So you can calculate the real power part of it and then the apparent power part of it, which we talked about. So the real power is always going to be the I squared R or E squared over R part of it that's in the horizontal axis. And the apparent power will be the magnitude of that vector, depending on what the phase angle is. In this one, so we have a 60 ohm load and a 160 millihenry inductor, which is also 60 ohms at 160 hertz. So that just goes through all the math for that. Calculating what the current is and what the phase angle and magnitude would be. So we're going to have impedance is going to be what, 60 plus J60 because it's inductance, so it's positive. And if you go do your arctangent, find out that it's 85-degree phase angle.
Bob,
I
I'm
think
getting
I
an awful
plotted
lot of
this
noise
thing.
up here. Something's banging the microphone.
Really?
Yeah, a lot of racket.
Maybe I'm talking too loud.
No, the talking's okay, but something mechanical is raising hell with the sound.
We don't hear it here.
It's gone now. Something was banging the
Okay.
microphone. It's okay now.
Let's see. If I move my mouse, does that do it?
No. Your speaking was not the problem. It was something mechanical hitting a microphone. Or,
Well, the microphone's hidden in my laptop somewhere.
or banging on a table, something or other. Something mechanical was making a lot of racket.
Okay.
It's gone now. Sorry to interrupt.
That's okay. This is a plot of the voltage and current in that previous circuit. You can see the difference in phase. Okay. It was what, 85 degrees? So it's not quite 90. And the actual power, where the blue line is apparent power and the yellow line is real power. And you notice that on the blue line, it's larger peak to peak, but it also goes below, goes negative. So that's the imaginary or reactive part of that power. The negative part and the part up here. So how many watts are consumed in a circuit consisting of a 100 ohm resistor in series with a 100 ohm inductive reactance drawing 1 ampere? It's a trick question. E5D. Times 1 squared. Amy? Let's see. Yeah, 1 squared times 100 is 100. Not two.
Maybe because of the series, and you were thinking add 100 to 100?
Sure. It asks for how many watts are consumed, so it would have to be real power. So the reactive part of it doesn't matter. Yeah, so. Okay. And talk about what happens when you have AC or RF energy in a circuit and things change from the nice world with 60 hertz or DC values. A wire, even if it's straight, will have some what they call self-inductance. And there's a formula that you can calculate what it is, and it's a function of the length of the wire and the diameter of the wire. and some other permeability or permittivity, whatever it is, constant. When you run a current through that wire, okay, it creates a magnetic field around the wire and an electrostatic field along the wire. So in most cases, you always will have an electric field and a magnetic field. So the higher the current going through the wire, the stronger the magnetic field is because it's a function of the current, changing current, because this only applies to alternating current. And that magnetic field actually is a circle around the conductor. In other words, it's like a cross product of the electric field, which is parallel. So that's why it's orthogonal to it and it goes around. And this diagram is trying to show you have the current represented by I flowing through this conductor, which is creating the blue magnetic field. Those are the magnetic lines of force. And they are actually creating little current loops around them, because as that magnetic field changes, it creates a current orthogonal to it. Well, if you notice the way those rotate, they're enforcing one another in the middle and on the outside. So it's tending to make the current appear or actually run closer to the outside of the conductor. We call that skin effect. And it's increases with increasing frequency. So the higher the frequency, which is more energy, because it takes more energy to cause something to oscillate at a higher frequency. The skin effect has more of an effect, and it has a thing called skin depth of how much of that outer surface is actually conducting current. So when you get to very high frequency stuff, it doesn't have to be a solid conductor because there's no current in the middle. It can be a tube. In fact, if you notice most of the antennas, the elements, as they get any size at all, become aluminum tubes because the current is going to be on the outside. Actually, you have the same kind of effect on very high voltage power lines because of the electric potential. It also does skin effect and forces the current to the outside. And if you look at some of these high tension power lines, when you go to Orlando or someplace, the really tall ones, and you'll see 3 or 4 wires with some like a spreader to get more surface area than having one big, tube or something. So this is a chart showing the skin depth at different frequencies. So you can see down here at 60 hertz, it's 8.5 millimeters, which is a larger than 1/4 inch diameter wire. So for anything smaller than, smaller than 8 millimeters, it's going to be completely in the conductor. As you get up to 100 megahertz, you're only getting what, 6/6,000ths of a millimeter. That's pretty small. So it's really just on the surface. And as you get even higher, it gets even less. That's why you see in a lot of high frequency stuff, you'll see flat conductors that are wide. So it has a lot of surface area, or in some cases, tubular ones. You always saw those on the old tube amplifiers and transmitters to reduce the inductance. And they use flat copper strap to connect from the plate to the tank circuit. This is just another one showing the same kind of thing. As you go up, that cross-sectional area becomes smaller. Likewise, the resistance of that wire goes up with increasing frequency because there's less cross-sectional area to conduct the current.
So I wondered why you were talking about not touching antennas, and that would be why, because it's more on the skin, what you're trying to.
Well, it isn't so much that as the fact that it could have thousands of volts on it. And you can get an RF burn, which I've been told is very painful. I haven't experienced it. I'm not going to go try. But they say it's not something you want to do.
That's what I've heard. And
Unless you're one of those crazy people on the TV stuff that go have spiders and stuff bite them to see.
right.
So there's a formula that you don't have to memorize for what the AC resistance is for a given frequency. And it is what they used, I think, to calculate that previous chart. But as you can see, it's a function of the square root of the frequency. There's just some examples over here for a 22 gauge wire at 100 megahertz, how much resistance it would appear to. So what is the result of skin effect?
A.
I was going to say, this is not a Charlie. Okay. A. As a conductor, oh, this is the famous question. As a conductor's diameter increases, what is the effect on its electrical length? This is a new question they threw in. The one I can't explain. I haven't found anybody else that explains it. I modeled a horizontal and vertical antenna in EasyNet and tried it and changed the diameter, and it lowered the frequency, which is consistent with the correct answer for this.
I would say if as the conductor's diameter increases, what is the effect on its electrical length?
Right. Remember, the electrical length is different than the physical length. It has to do with the velocity factor of how fast a wave moves through that conductor, which is a function of its dielectric. Okay. And inductance. The only thing I've been able to not totally prove, if you increase the diameter of a conductor,
Yes.
the inductance decreases. The larger, the more surface area in the inductance formula, the inductance goes down. But also increasing the diameter increases the surface area. So if you calculate the capacitance, the stray capacitance from that conductor, it's going to increase. It looks like it increases by a factor of 3 compared to the decrease of the inductance. So the product of the two becomes greater. And the resonant formula is, remember, 1 over 2 pi times the square root of LC. So if LC is a bigger number, then the resonant frequency result is going to be less because you're dividing it by a bigger number. But I can't necessarily prove that either. So this is
Bob?
the answer is D, it increases. Most people guess C.
Mhm.
And I
Bob?
don't know why, but that's the way it is. I can prove it with a model. There's other examples that show that that's the effect. I can't explain the physics.
It's happening at dot button.
Yeah,
So maybe, as a conductor gets bigger, right, you usually get more distance out of something. So in even network cable, right? If you want to get networking power like a Cat 6 cable versus a Cat 5 cable and stuff, the conductors are bigger. You get more bandwidth at the end of the thing. I feel like it's better performance. And so that's why I thought increases was just because, right, you've got a bigger conductor, 48U versus 58 or something like that. You're basically saying you're getting more power at the other end of the
well, the basic difference with those coaxes is the physical size larger, you have less loss.
right.
Right.
So this almost follows. I feel like follows that, but not from the
Yeah, I don't know. They put it in with the skin effect stuff, which kind of makes you think it has somehow related to skin effect, but I don't know how that figures in. Because skin effect affects the effective resistance. And as far as I know, resistance doesn't affect the electrical link. So I don't know. It's just, that's the answer. If you get that question, it increases. Okay, so we talked about inductors and capacitors storing energy. And in a resonant circuit, they just transfer it back and forth between the two. Nothing really new there. There's a skin effect that also affects things like film capacitors. And as you increase frequency, it has more of an effect. And this is a chart I found showing at different frequencies what the effective resistance is in those. It's a 22 picofarad film capacitor, fairly standard type.
Bob?
So what is the primary cause of loss in film capacitors at RF? Skin effect. Now, you also have electrolytic capacitors, which have a little different effect because you can have inductance due to the way they're actually manufactured in the leads. They're typically wire leaded devices. So as the frequency goes up, you have more of an effect from the inductance as part of that capacitor, because in the real world, all capacitors have some inductance and some series and parallel resistance. And this chart is kind of showing over the frequency range what happens as you approach the resonant frequency of those parasitic components, the capacitor itself, and that inductance in the leads and the pack in the way the electrolytic conductor itself is made. And the skin effect part of it affects the effective series resistance. So that's why it doesn't go to zero like it would if it was a perfect capacitor. So it's going to have some bottom out at that ESR value. So what parasitic characteristic causes electrolytic capacitors to be unsuitable for use at RF?
No, you just said it would have parasitic inductance.
Okay, if I have an inductor, okay, we know that it stores energy in the magnetic field, okay? And because it's typically gonna be in a coil form, where you have turns wrapped around the toroid or in the air or whatever. You have parasitic capacitance between the windings, they call it interwinding capacitance. The closer those windings are together, the more the capacitance. As you spread it out, the capacitance decreases, but so does the inductance. Because part of the inductance formula is how many turns, how close together they are, what's the area inside. If we look at the frequency plot for that inductor, we can see that, there's a resonant point because you've got L and C with the parasitic components, the interwinding capacitance and the inductance itself. So it's going to resonate at some frequency. And then you've got some effective series resistance in there, which is going to affect the Q of that. So it will affect how sharp this curve is that they're showing. And there's the formula again for resonance that I copied that one. That's supposed to be a pi sign. I'm not sure what it is.
Just looks like you got a little trim on the edges there.
So what parasitic characteristic creates an inductor's self-resonance? Interturn capacitance. What combines to create the self-resonance of a component? You have to read this one carefully.
Maybe B.
It might be B. We'll have to wait and see. And that does, I don't mean that C.
We could wait and be
What it be? Yeah,
to be or not to be.
it's the nominal, whether it's an inductor or capacitor, and then it's parasitic reactance, which in the case of the capacitor, well, you could have both additional parasitic capacitance and inductance, but it's the combination of all of those that's going to determine the resonant frequency. So when we go up to really high frequencies, that's where the length of conductors starts to have an effect. Not only just the inductance, because the inductive reactance goes up with frequency. The length of it can affect the phase shift. When you start getting links that are a wavelength or a fraction of a wavelength, excuse me, the other way around, a wavelength or longer than a wavelength, then you're going to see phase shifts along the length of that. Just because it takes time for that sine wave to move through the conductor. So when you're doing very high frequency stuff, one of the things you have to look out for is the actual wiring and the lengths of connectors. And it gets to the point where for certain things, you have to make sure that the path lengths are exactly equal, so you don't have a phase shift between them. So why is it important to keep lead length short for components used in circuits for VHF and above?
Well, It's not A. It's not C.
Well, if it's not A, it can't be D. So you're down to B and C.
So it's B.
Yeah. Why are short connections used at microwave frequencies?
Beanie.
Reduce phase shift. When you get in microwaves, you're talking about wavelengths that are uh, fractions of a meter. You're down to below centimeter wavelengths. Even at UHF, 70 centimeters is not that, it's what, 16, 18 inches, something like that.
And those short connections reduce the reactance, which in turn causes the phase shift. Is that gonna,
Right. Well, the length of it is part of the phase shift at the frequencies, but you also want to reduce the reactance or the inductance. And usually in those kind of things, they will use what's called microstrip or strip line, where you actually are kind of making a little transmission line that has a constant impedance by the width of it and the thickness of it between the ground plane and the conductor, or it might be a sandwich where you got a ground plane on both sides of it. Kind of like building a little coax. So we learned that reactive power is wattless. It dissipates no power, doesn't do any work. There's no energy that's dissipated. Remember Eli the Iceman. Skin effect goes up with frequency, and it can affect capacitors as well as inductors, but mostly some of the capacitors, which is why they don't work as well at very high frequencies, especially electrolytics. And that you care about phase shift when you're doing UHF and microwave things because of the length of the conductors, not only the inductance, but just the length of it starts to approach the wavelength of the signal itself.